Transverse Thomson effect observed experimentally, new frontiers in thermal management. In a groundbreaking revelation that could revolutionize thermal management, researchers have unveiled the experimental observation of the transverse Thomson effect, a thermoelectric phenomenon that has eluded scientists for nearly a century. This discovery, published in a recent online paper, has the potential to unlock new possibilities in the field of heat and electricity interaction. Let's delve into the details of this fascinating breakthrough and explore its implications for future research and applications. The transverse Thomson effect, a higher-order thermoelectric effect, was observed when the electric current, magnetic field, and temperature gradient interact in a perpendicular manner. Led by Atsushi Takahagi, the research team successfully isolated the signals by applying temperature modulations and periodic electric currents. Through meticulous measurements, they managed to separate the Thomson effect from overlapping signals, marking a significant milestone in thermoelectric research. To demonstrate the effect, the team utilized a bismuth antimony alloy, known for its strong Nernst effect at room temperature. The Nernst effect occurs when a temperature gradient and magnetic field are applied orthogonally, generating an electric field perpendicular to both. Conversely, the Atting-Shawsausen effect creates a temperature gradient from the interaction of magnetic and electric fields. The researchers discovered that the transverse Thomson effect is dependent on the temperature derivative of the Nernst coefficient, a finding that sets it apart from conventional thermoelectric effects. One of the most intriguing aspects of this discovery is the ability to switch between heating and cooling by simply altering the direction of the magnetic field. This interplay between the magnetic field and the effect resulted in a reversal of the sign at varying magnetic field strengths, a phenomenon confirmed through both experiments and numerical simulations. The implications of this discovery for thermal management are vast, particularly in applications requiring controlled heat. Future research may focus on identifying new materials where the gradients of the transverse Thomson coefficient amplify each other, rather than cancelling out, indicating high-performance thermoelectric materials. This could lead to the development of more efficient and versatile thermal management systems. Stay tuned for more updates on this exciting development in thermoelectric research. For the latest tech news and reviews, follow Gadgets 360 on various platforms, including X, Facebook, WhatsApp, Threads, and Google News. Subscribe to our YouTube channel for the latest videos on gadgets and technology. And for insights into top influencers, check out our in-house Who S That 360 on Instagram and YouTube. Physics breakthrough, transverse Thomson effect observed after 174 years. ****, a groundbreaking discovery in physics. The 174-year-old Thomson effect finally observed. In an exciting development, researchers from Japan have made a significant breakthrough by observing the transverse Thomson effect for the first time. This thermoelectric phenomenon has the potential to revolutionize how we manage heating and cooling processes. Updated, July 21, 2025, 09:06 AM EST***. Imagine a world where a device can seamlessly switch between heating and cooling a specific area simply by altering a magnetic field. This innovative approach could eliminate the need for separate heating and cooling units or the cumbersome process of reversing current directions, as is done with traditional Peltier coolers. The implications of this discovery could be transformative. Understanding the Thomson effect. The foundation of our knowledge regarding the interaction between heat and electricity dates back to the 19th century. At that time, scientists could only hypothesize about the existence of the transverse Thomson effect, which describes the relationship between the flow of electric current and temperature gradients. Now, for the first time, Japanese physicists have provided concrete evidence of its existence. The research team's findings. In a study published in Nature Physics*, a team led by Atsushi Takahagi from Nagoya University and Kenichi Uchida from the University of Tokyo reported their groundbreaking findings. They successfully observed the transverse Thomson effect in a semimetallic alloy known as Bi-88Sb12 using thermoelectric imaging techniques. The researchers explained, "Our experiments and analyses reveal the essential difference between the conventional and transverse Thomson effects. While the former relies solely on the temperature derivative of the Seebeck coefficient, the latter is influenced by both the temperature derivative and the magnitude of the Nernst coefficient. This observation opens up new possibilities for active thermal management technologies. Challenges in observation. Historically, physicists faced challenges in observing the transverse Thomson effect due to interference from competing thermal effects, specifically the Peltier and Ettinger-Thomson effects. However, the researchers' choice of materials played a crucial role in their success. They utilized a semimetal conductor made from bismuth and antimony, which is known for its strong Nernst effect at room temperature. By applying an electric current and a magnetic field at right angles to a sheet of by 88 Sb12, they were able to observe both heating and cooling effects. This specific material was particularly well suited for achieving the desired outcomes. Instead of applying heat to the ends of the material, they directed it to the sides while the magnetic field was applied from above. Innovative techniques for measurement. To overcome the challenge of signal isolation, the Japanese researchers employed an infrared camera to monitor the thermal response of the sample when a periodic electric current was applied. They explained, by extracting the temperature modulation component that oscillates at the same frequency as the applied current from the thermal images, we successfully isolated the thermoelectric signals from the Joule heating. Once they identified that the spatial distribution of the transverse Thomson effect differed from other competing effects, they conducted measurements both with and without a temperature gradient. By subtracting these results, they were able to isolate the pure transverse Thomson signal. Surprising results and future directions. To their astonishment, the researchers discovered that they could switch between heating and cooling simply by changing the direction of the magnetic field. This finding has the potential to enhance the efficiency of transverse thermoelectric cooling devices significantly. Looking ahead, the researchers are committed to exploring materials that are most conducive to producing the transverse Thomson effect. They believe this area of study will be a vital focus for future research. Join the discussion. What do you think about this groundbreaking discovery? Could this technology change the way we approach heating and cooling in our daily lives? Share your thoughts in the comments below. Read the full study in Nature Physics here. https://www.nature.com/articles/S41567-025-02936-3 About the author Maria Mosserino, originally from Los Angeles, has contributed to various publications, including Business Insider and the Irish Examiner, and is currently writing for Interesting Engineering. Scientists observe transverse Thomson effect for the first time. Imagine this, a century-old mystery in physics has finally been unraveled, and it's not just any mystery, it's one that could revolutionize how we manage heat and electricity. Scientists have just made the first-ever experimental observation of the transverse Thomson effect, a thermoelectric phenomenon that has baffled researchers since its prediction over 100 years ago. But here's where it gets controversial. The implications of this discovery could be enormous, but so are the challenges in understanding and harnessing it. Let's dive in. For over a century, thermoelectric effects have been the bedrock of our understanding of how heat and electricity interact within materials. These interactions are primarily explained by the Seebeck, Peltier, and Thomson effects, all of which were identified during the 19th century. The Thomson effect, in particular, is fascinating because it causes volumetric heating or cooling when an electric current and a temperature gradient flow in the same direction through a conductor. But this is the part most people miss. Scientists have long theorized that there should be a transverse version of the Thomson effect. This version would occur when an electric current, temperature gradient, and magnetic field are applied in perpendicular directions within a conductor. Until now, this effect has remained elusive, hidden behind a veil of competing thermal effects like the Peltier and Ettinger-Thomson effects. Now, a groundbreaking research team led by Atsushi Takahagi from Nagoya University and Kenichi Uchida from the University of Tokyo has finally demonstrated the existence of this transverse effect. This discovery is a significant milestone in the field of thermoelectric effects, opening up new avenues for energy harvesting and thermal management technologies. The thermoelectric effect has always fascinated me, especially its potential in energy harvesting and thermal management, Takahagi shared with PFS.org. This enthusiasm is palpable in their work, which has not only confirmed the existence of the Transverse Thomson effect but also provided a method to isolate its signal from other thermal effects. The challenge of isolating the Transverse Thomson effect was monumental. To overcome this, the research team employed advanced thermoelectric imaging techniques, specifically lock-in thermography. In our experiment, we used an infrared camera to observe the thermal response of the sample when a periodic electric current was applied, Uchida explained. By extracting the temperature modulation component that oscillated at the same frequency as the applied current, they were able to isolate the thermoelectric signals from the Joule heating. The turning point came when the team recognized that the spatial distribution of the Transverse Thomson effect differed from other competing effects. They performed measurements under two conditions, with and without a temperature gradient. By subtracting the results, they successfully isolated the pure Transverse Thomson signal. The first measurement captured both the Transverse Thomson effect and the Attingshaw-Sawson effects, while the second measurement, without the temperature gradient, captured just the latter. Subtracting the second from the first yielded the isolated Transverse Thomson effect. Choosing the right material was crucial. The researchers selected a bismuth antimony alloy, by 88Sb12, known for its strong Nernst effect around room temperature. The Nernst effect occurs when a temperature gradient and magnetic field are applied orthogonally to a material, creating an electric field perpendicular to both. The Attingshaw-Sawson effect, on the other hand, is the reverse. When an electric current and magnetic field are applied orthogonally, a temperature gradient is created perpendicular to both. Our research revealed that the magnitude of the heat source responsible for the Transverse Thomson effect is determined by both the temperature derivative of the Nernst coefficient and the Nernst coefficient itself, Takahagi explained. The Bi-88Sb12 alloy, with its large Nernst coefficient, proved to be an ideal candidate for exhibiting the Transverse Thomson effect. This is a fundamental difference from the conventional Thomson effect, which depends solely on the temperature derivative of the Seebeck coefficient. One of the most surprising discoveries was the ability to switch between heating and cooling by simply changing the magnetic field direction. The effect showed complex field-dependent behavior, including a complete sign reversal at certain magnetic field strengths. The researchers discovered that the Transverse Thomson coefficient comprises two competing components, one related to the temperature derivative of the Nernst coefficient, generally causing heating, and another related to the Nernst coefficient magnitude, generally causing cooling. The competition between these components creates the field-dependent sign reversal observed in their experiments. Their numerical simulations accurately reproduced the experimental observations, confirming the theoretical understanding of the phenomenon and validating their measurement technique. The discovery opens new possibilities for thermal management technologies, particularly in applications requiring precise, localized heat control. In recent years, it has been reported that the conventional Thomson effect can enhance the performance of Peltier cooling, noted Takahagi. Similarly, the Transverse Thomson effect is expected to serve as a principle for improving the performance of transverse thermoelectric cooling devices. The current work also points toward strategies for developing more efficient materials. In the Bi-88Sb12 alloy studied, the two components of the Transverse Thomson coefficient partially cancel each other out, limiting the overall magnitude of the effect. Identifying new materials in which these two components reinforce each other could lead to the discovery of high-performance materials for the Transverse Thomson effect, representing an important avenue for future research, explained Uchida. This article is the result of careful human work by our author Tejasri Guru-Raj, edited by Lisa Locke, and fact-checked and reviewed by Andrew Zinin. We rely on readers like you to keep independent science journalism alive. If this reporting matters to you, please consider a donation, especially monthly. You'll get an ad-free account as a thank you. For more information, you can refer to the original paper, at Sushi Takahagi et al., Observation of the Transverse Thomson Effect, Nature Physics, 2025. DOI 10.1038S41567-025-02936-3. Now, here's a thought-provoking question for you. Do you think this discovery will lead to significant advancements in thermal management technologies, or are there still too many unknowns to predict its impact? Share your thoughts in the comments below and let's spark a discussion.